In this problem, we're told that we have a particle moving in one dimension accelerating with a linearly increasing acceleration. So this is no longer constant acceleration kinematics. Our acceleration is actually a function of time that we write as kt, where we're told that k is a constant that has the right units on it to make this work out to units of acceleration. We're also going to stay very general here about what to call the initial position. I'm calling that x naught, and the initial velocity v naught. And so the point of the problem is that we want to derive the equations of motion for this object. That's the velocity as a function of time and the position as a function of time. And because this is a non-constant acceleration, we have to start with the very fundamentals here. And the way we start this derivation is we say, well, the time derivative of the velocity function, that's the acceleration. So I can say that v prime of t is equal to kt. Well, it's not hard to guess what v is here. V of t is the thing I differentiate to get kt. In other words, the antiderivative. So I end up with 1/2 kt squared. But to be as general as possible, we've got to put a plus c in there. Now this is where the initial conditions come in. If I look at v of 0, well, this 1/2 kt squared term dies because replacing t with 0, I get 0 out of that. And then we realize that v of 0 is just c itself. So another name for c is v naught, the initial velocity. Okay, so we actually have our first equation of motion already. V of t is going to be v naught plus 1/2 kt squared. So now we just repeat this process where we start with the fact that x prime of t, the derivative of our position function, that's what we call the velocity. So x prime of t, that's v naught plus 1/2 kt squared. And again, we're just guessing an antiderivative to get x of t itself. So x of t is going to be v naught t. And then when I find the antiderivative of t squared, that's t cubed over 3. So I end up with a 1/6 kt cubed plus an arbitrary constant. And then a very similar thing happens here. X of 0, that's our initial position. When I sub in t equals 0, both of these terms are gone, leaving me with only c. So another name for c is actually the initial position, x naught. And we sub this into our expression for x of t. So I have x of t equals, I'm going to write this term first, x naught plus v naught t. That looks very similar to the constant acceleration case. And then I have my final term that looks different from the constant acceleration case. I end up with this cubic thing, 1/6 kt cubed, because our acceleration was increasing linearly. So if we think back to what the constant acceleration case looked like, our velocity function was linear. It was v naught plus at. Well, now the velocity function is quadratic because we had to find the antiderivative of a linear acceleration. We also remember that our position function was quadratic. It was x naught plus v naught t plus 1/2 at squared. And now it's cubic because we found two antiderivatives of a linear acceleration function. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.